Welcome back to Calculus 30. Today I want to have a look at section 4.2, which is the last section of notes for this particular chapter. I need to stop and go backwards a little bit. If you watch the section 4.1 video, you might have heard me keep saying the expression first derivative. I need to go back and talk about Physics 30 for a second. And for those of you who took Physics 30, you will have seen this quite a bit. In Physics 30, Miss Tuplin was always drawing three graphs. And if you didn't take Physics 30, it's not the end of the world. In Physics 30, you looked at distance versus time, velocity versus time, and acceleration versus time graphs. And we said, if you wanted to go from distance to velocity, you had to do a slope calculation. And another word for slope is derivative. And then if you had a velocity versus time graph and you wanted to find acceleration, to go from velocity to acceleration, you had to do another slope calculation, or what I'm going to now call the second derivative. So in calculus, if we have a function f of x equals, it doesn't matter what it equals. It can be any expression over here. If I take the derivative, we called it f prime of x, which is another way of saying y prime. But if I take the derivative again, I get something called the second derivative, or f double prime of x, which can be rewritten as y double prime. So if I move forward, if I did a quick example, if I had a function f of x equals 4x to the power 7 minus 3x to the power 5 plus 2x cubed plus 17, I could find my first derivative, f prime of x. And using the power rule, 7 times 4 is 28. Subtracting 1 from the exponent, that would be 28x to the 6. Minus 5 times 3 is 15. Subtracting 1 from the exponent, that's x to the power 4. Plus 3 times 2 is 6. Subtracting 1 from the exponent, 6x squared. And the derivative of any constant is 0. Now, I could take the second derivative, f double prime of x, by just applying the power rule again. So 6 times 28, I would pick numbers that are large. 6 times 8 is 48, carry the 4, 12 and 4, that's 168 x to the power 5 minus 4 times 15 would be 60 x cubed, and 2 times 6, this would be 12x. And if I wanted to, I could actually take the derivative one more time. I could go f triple prime of x and just keep applying the power rule. So we can go f prime of x, f double prime, f triple prime, f quadruple prime. We can keep taking the derivative of the derivative of the derivative, and so on and so on and so on. So in the 4.1 video, I tried to avoid saying the first derivative, but when you know what's coming up, today we're going to look at something called the second derivative test. We are going to be focusing on this second derivative, and it comes from Isaac Newton. When Isaac Newton developed calculus, he knew that we would take the derivative to get from distance to velocity, and then we would take the derivative again to get from velocity to acceleration. So that's what we're going to be doing today. Now, before we get there, I just want to go through and clear off these pages. All right. Let's start today's notes. Today's notes begin with a picture that looks like this. If you go back to the Google Classroom, I have this diagram. And so I've tried to reproduce it here, drawing it freehand on this page here. So I want to focus for now on this section. If I look at this section, I have a local or relative maximum at this point. So if I look at this section of the graph, this section of the graph kind of looks like a parabola that is concave down. Now, if I go over here, I have a minimum value. And if I look at this section of the graph, it kind of looks like a parabola that is concave up. So on the left, I started with a section that was concave down, and I'm going to abbreviate that capital CD. And over here, I have a section of the graph that is concave up. I'm going to abbreviate that capital CU. So that means at some point, our concavity had to have changed. So I'm going to draw a point here. And I am going to say that this is the point where we switched from concave down to concave up. And we refer to that as an inflection point. An inflection point is where we change from concave down to concave up. So here we are, statement number 1, the concavity of a graph changes at the inflection points, abbreviated capital I, capital P, or some textbooks refer to it as the point of inflection, POI. Some calculus teachers call them POI points, POI, POI, point of inflection, or capital IP inflection point. I'll probably switch back and forth between them, so you should know what both abbreviations refer to. How do we find inflection points? Well, this is where it's important that we understand the second derivative. Inflection points are found by taking the second derivative, f double prime of x, setting it equal to 0, and solving. Now, the second derivative also gives us another handy test. We have something called the second derivative test. If, and let's get my spotlight out here for this. If I have a critical point C, the critical point C will be a relative minimum if I take that C value and substitute it into my second derivative and get a positive answer. If I take my critical value, substitute it into the second derivative and get a positive answer, it will be a minimum. If I take my C value, substitute it into my second derivative, and my answer is negative, that means that that critical point is going to be a maximum. And after we do a couple examples, you'll see how easy this is to deal with. And then our fourth statement, functions are increasing or decreasing according to the position of the maximums and minimums. So again, what does that all mean? Well, probably at this point, it doesn't mean a whole lot to you, but after we do a couple of examples, you will see how simple this is to deal with. So that's it for notes today, but we have 3 rather long examples. So I'm going to do 2 examples, and then I'll probably stop the recording, post it, and then I'll do another example and post that later. I guess you can take a break anytime you want. All you have to do is hit pause, get up, go get a drink of water, have a snack, have a nap. I don't care what it is. That's the great thing about these videos. In class, you're stuck listening to me until the bell rings. But here, if you're bored or distracted or just need a break, hit pause, come back to the video. Maybe I'll experiment with that. I'll hit pause, go into the house. It's getting close to lunchtime here for me. So maybe I'll experiment with that. All right, enough rambling. Where's my mouse? Let's look at this example. Graph y equals x cubed plus 3x squared. We want to graph y equals x cubed plus 3x squared. Now I have taken the liberty of putting that into this scribbler, and I want to work through the process. I'm a big believer in physical memory. I really, really hope that you're not just printing off the notes and following along with the video. You should have a blank pad of paper and a pencil or a pen, and you should be working through this with me. Now notice I've changed it from y equals x cubed plus 3x squared to f of x equals x cubed plus 3x squared. And there's a reason for that, and you'll see it as I go through the next 2 or 3 examples. So if I was being asked to graph this, the first thing I would want to do is I always want to find my critical points. And so I abbreviate that CRT PTS, critical points. And that's what we were doing in section 4.1. To find the critical points, the first thing I have to do is find my first derivative, f prime. And so I'm just going to use the power rule. The derivative of x cubed is 3x squared. The derivative of 3x squared is 6x. Once I have this, I take my first derivative and set it equal to 0. 0 equals 3x squared plus 6x. And now I need to solve this equation. This is a quadratic, and all quadratics are solved by factoring. So I'm going to take out a GCF. Both of these terms are divisible by 3x. And if I factor that 3x out, I'm going to be left with x plus 2. Now, I'm going to need to solve this. I have my first factor, which is 3x, times my second factor, which is 3x plus 2. So I'm going to take my first factor, which was 3x, set it equal to 0. I'm going to take my second factor, which was x plus 2, and set it equal to 0. If I solve this, dividing both sides by 3, x would equal 0. Taking the, that's a very terrible 0. If I take the plus 2 over and subtract, x would equal minus 2. So I have 2 possible x values. Now, if I'm going to graph these, I need to find their corresponding y values. Now, in order to do that, I'm just going to substitute back into the original equation. And if you follow along on the notes, that's what I did. If x equals 0, now I'm going to substitute back into the original and find f of 0. So the original equation was x cubed, so that'll be 0 cubed, plus 3x squared, so that will be 3 times 0 squared. And that's 0 plus 0, which is 0. So I am going to have a critical point at 0, 0. There is one critical point. Now I need to find my second one. So I'm going to go to a new page. If my x value is minus 2, then f of minus 2 is going to be minus 2 cubed plus 3 times minus 2 squared. Simplifying this, minus 2 cubed. Now notice I used parentheses here. I have to cube the minus sign as well. That's minus 8. Here, order of operations, I do exponents first. Minus 2 squared is 4. 4 times 3 is 12. And minus 8 plus 12 is 4. So I have another critical point at minus 2 and 4. So I have two critical points. I found my first critical point here at 0, 0, and I found my second critical point at minus 2 and 4. So once I have my critical points, now what I want to do, the second thing I always do is test my critical points. And in order to test my critical points, I need to find my second derivative. So I'm just going to remind you, my first derivative we found already. My first derivative was 3x squared plus 6x. We've done that already. So now I take my second derivative, f double prime. And again, I'm just going to use the power rule. 2 times 3 is 6. That will be 6x plus 6. There's my second derivative. Now I can actually take and quickly copy this. So I am going to copy this, go to the next page and paste it. There's my second derivative. So how do I use this to test my critical points? Well, if I go back to page 4, oh, sorry, I need to go back one more. Page 3, I had a critical point at 0, 0. My x value was 0. Let's highlight this. I had an x, I had an x value at 0, and I had an x value at minus 2. So now I'm going to go forward. Here's my second derivative. So now what I'm going to do is I am going to substitute the 0 into my second derivative. So that's going to be 6 times 0 plus 6. 0 plus 6 is 6. Now I don't actually care that my answer is 6. What I'm more concerned with is the fact that this answer is positive. And if I go back to my notes, and that's what I want to do now, I'm going to click back here. If I go back up here, it said this: if I substitute a number into my second derivative and that answer is positive, that means this critical point is a minimum. So there is a minimum at 0, 0. So if I go back to my scribbler, if this is a positive value, we are saying 0, 0 is a minimum. Let's undo that. Minimum. 0, 0 is a minimum. Now I'm going to go forward and I'm going to test f double prime. My other x value was minus 2. So substituting into my second derivative, that's 6 times minus 2 plus 6. Minus 12 plus 6 is minus 6. Now again, I don't care specifically that the answer is minus 6. I'm more concerned that this answer is negative. And if I go back to my notes, if I substitute into my second derivative and my answer is negative, that's because our critical point is a maximum. So going back here, we had, let's go back to the colored black. We had a critical point at minus 2, 4, and it's going to be a maximum because when I substituted into the second derivative, I got a negative answer. Well, we're not done yet. We found our critical points. We have tested our critical points. Now, our third step is to always find inflection points. And inflection points are found by taking the second derivative, which was 6x plus 6, and setting that equal to 0 and solving. If I go back to my notes, that's what it said here. Inflection points are found by setting the second derivative equal to 0 and solving. So let's do that. If I take this plus 6 to the other side and subtract, that's minus 6 equals 6x. And if I divide both sides by 6, x equals minus 1. Well, we are finding inflection points. Every point has an x and a y value. So now I have to take this x value equals minus 1 and substitute it back into the original function f. So I'm going to find f of minus 1. So the original function was x cubed, so that's minus 1 cubed plus 3x squared, so 3 times minus 1 squared. So that's going to be minus 1. Minus 1 squared is 1 times 3 is 3, and minus 1 plus 3 is 2. So that means I have an inflection point at an x value of minus 1 and a y coordinate of 2. So now what I need to do is graph this. So I can draw a very rough coordinate axis. So there's my y-axis. Here's my x-axis. Whoops. So labeling x, labeling y. Now what I've done is I've gone to Desmos ahead of time and plotted an x and a y axis. Notice I have an arrow going to the right and my horizontal axis is labeled x. I have an arrow going up, my vertical axis is labeled y. And if I go back through the steps we did, we had a critical point at 0, 0. We had a critical point at minus 2 and 4. And I had an inflection point at minus 1 and 2. So I have these 3 points. Now, when we calculated the minus 2, 4, when we tested the minus 2, 4, that was a maximum. And when I tested the 0, 0, that was a minimum. If I go back to my scribbler, sorry, 0, 0, okay, sorry, there we are. 0, 0 was a minimum. 0, 0 was a minimum. So if I go back to my graph, this is a minimum. So this section of the graph has to be concave up. So if I were going to freehand this, and I shouldn't, let's not freehand this, not on the Desmos, let's go here. At 0, 0, I have a minimum. So if I was going to freehand it, this section of the graph would look like that. At minus 2, 4, that was a maximum. That's concave down. So this section has to look like this. There's my inflection point. My inflection point was at minus 1, 2. This section is concave up. This section is concave down. So if I go back to Desmos, There's my graph. Minus 2, 4 was my maximum. Minus 1, 2 was my minimum. Was my inflection point. 0, 0 was my minimum. Now I'm going to stop here. This has nothing to do with calculus. This is just a Desmos tip. If you go into that wrench icon, you can turn your grid on or off. I turned it off for this so that it would be less distracting. The other thing you can do is you can label your x-axis. I labeled this x, I labeled that y, and then you can also turn your arrows on or off and have them on all four or just going to the right or going up. So that's something you can do to make your graph less cluttered when you're using Desmos. So again, maximum at minus 2, 4, minimum at 0, 0, and my inflection point was in the middle. That's where it changed from concave down to concave up, which completes my first example. I almost caught myself asking, does anybody have questions? Well, maybe you have questions, but obviously you're not going to interrupt the lesson and ask them. Let's do one more example. At this point, you may want to pause the video, get up and go for a break. I'm actually going to try that. Alt-T. Let's pause the video. All right, I'm back after a short break. I went in, made myself lunch, went for a 5-kilometer run on the treadmill, and did a workout. I can't even say that with a straight face. Who am I trying to kid? I went in, had lunch, and had a nap. All right, let's finish up this lesson. We finished the first example. We're talking today about inflection points, the points at which a graph changes from concave up to concave down. So let's look at our second example, and it's tough to find examples where the numbers work out nicely all the time. So if we look at the next example, we have the expression f of x equals x cubed minus 2x squared plus x plus 1. We would like to be able to graph this question. So I'm going to go back to the scribbler and let's start a new page. Let's get back to the color black. And we have the graph. And I'm going to change back to f of x notation. F of x is equal to x cubed minus 2x squared plus x plus 1. So that's our function, and we would like to graph this. And we can do it very, very simply using calculus. The first thing I always like to find are the critical points. And we find the critical points by taking our first derivative, f prime of x. So using the power law, this will be 3x squared minus 4x plus 1. To find the critical points, we take our first derivative and set it equal to 0. So 0 will equal 3x squared minus 4x plus 0. The derivative of any constant is 0. Well, what am I doing? I didn't even take the derivative. What a maroon. So, all right, let's try that again. Oh, wait a minute. I kind of did this right. 0 equals 3x squared minus 4x. Sorry, I had taken the derivative. That nap, apparently I haven't woken up yet. So 0 equals 3x squared minus 4x plus 1. Well, this is a quadratic. It's a trinomial. And where does every trinomial in the universe come from? Every trinomial in the universe comes from two binomials. Now, to factor this one, it should be fairly easy. The only way to get 3x squared is 3x times x. And the only way to get 1 is 1 times 1. And if my middle term is going to be minus 4x, both of those terms have to be negative. And if we do a binomial expansion and check this out, we'll have 3x squared minus 3x on the outside minus 1x on the inside gives me a middle term of minus 4x. and minus 1 times minus 1 is plus 1. So either my first factor equals 0 or the second factor equals 0. Solving the second factor is easy. If I take the minus 1 over and add, I get x equals 1. Here I'll have to do 2 steps. I'll add 1 to both sides, 3x equals 1. Dividing both sides by 3, x equals 1/3. Well, I have 2 possible x values, which means I need to find 2 possible y values. So I'm going to substitute. If x equals 1/3, then y is going to equal. So now we're going to substitute back into the original, and this is grade 9 algebra. I'm not going to show you how to do this. Let's go back to the notes that I've posted on the Google Classroom. So I have my x value of 1/3. I've substituted it into the original y equation. When you're trying to find the y coordinate, you always go back to the original y expression. And it's going to be ugly. It's going to be fractions. We're going to have 1/3 cubed minus 2 times 1/3 all squared plus 1/3 plus 1. So finding a common denominator, well, you guys all have advanced scientific calculators. You could just punch this into your calculator. If you do it properly, you should get the value 31 over 27. So we have a possible critical point at 31 over 27. And then when I substitute 1 into the original expression, maybe I should emphasize this a little bit more. So if x equals 1, that was the second c value we got. Substituting that into the original expression, we have a critical point at 1, 1. So we have 2 critical points, 1/3 and 31 over 27, and 1, 1. So now we need to test our critical points. So to test our critical points, we are going to take the x value of 1/3, the x value of 1, and substitute them into our second derivative. So I'm going to go back to the scribbler, because this is the new material. So I'm going to work through this with you. So just to remind ourselves, our first derivative, f prime of x, was 3x squared minus 4x plus 1. So when I take my second derivative, f double prime of x, using the power rule, this will be 6x minus 4. I have 2 x values to test. The first one was f double prime of 1/3. 1/3. So if I substitute 1/3 in, that will be 6 times 1/3 minus 4. Well, 6 times 1/3, 3 goes into 6 2 times. That's 2 minus 4, which is minus 2. So I'm not concerned that the actual value is minus 2. What I want to emphasize here is that minus 2 is a negative number. So if minus 2 is a negative number, that tells us our critical point, which was at 1/3 and 31 over 27, is going to be a maximum. That's what the second derivative test tells us. If I take my critical value, substitute it into the second derivative, and I get a negative answer, that critical point is a maximum. So let's test our next point. If I take f double prime of 1, sorry, let's switch back to black. That's going to equal 6 times 1 minus 4. So that's 6 minus 4 is plus 2. 6 minus 4 is a plus 2. So that tells me my critical point which was at 1, 1, has to be a minimum. If my second derivative is positive, this point is a minimum value. All right, we found our critical points. We tested our critical points. Our third step is to find the inflection points, or points of inflection. And to do that, we take our second derivative, f double prime of x, which was equal to 6x minus 4, and we set that equal to 0. 0 equals 6x minus 4. So if I substitute that, adding 4 to both sides, I get 4 equals 6x. Dividing both sides by 6, I get x equals 4 over 6, and that would reduce to 3 over 2. Now again, I'm going to switch back to my notes. We need to find the y value for this inflection point. And this is a straight substitution back into the original f of x function. So again, that's just grade 9 math. Why? Was there a problem loading this page? Let's hit refresh and see what happens. All right, so we were looking at graphing. We are doing section 4.2, second derivative test. Sorry, I guess I should have woke my computer up after I took that little break there. We are doing the notes. Let's fit this to the page width. All right, so there's our second example. We found our critical points, we tested our critical points, and now we're finding the inflection points. So I got an x value of 2/3. Is that what I put? No, I didn't. What a dummy. 3/2. That reduces to 2/3, dummy. All right. Now if I go back to my classroom, that has been more painful than necessary. So I took the 2/3. Let's bring my spotlight back. There's my x equals 2/3. I substituted it back into the original y equals equation. So we're dealing with some ugly fractions here. Finding a common denominator and getting an answer, we have an inflection point at 29 over 27. Now, these points have not been at all pleasant to work with. We have an inflection point at 2/3 and 29 over 27. Our critical points were at 1/3 and 31 over 27, and we had one nice point, 1, 1. Well, how do we graph this? Well, let's go back to our scribbler for a second. Let's go to a new blank page. Let's draw a coordinate axis. Now remember, when you draw a coordinate axis, you get to set the scale. So if I look at my numbers, none of my numbers are they're all right around 1. We had 1, 1 as a point. We had 1/3 and 31 over 27. We had 2/3. And what was the coordinate there? 2/3 and 29 over 27. So everything seems to be around the number 1. So if I was going to set up my scale, I'd put a 1 there, a -1 down here, a +1 over there, and a -1 back there. I would set up my scale like that. So now when I set up my points, my first point had an x value equal to 1/3. Well, if this is 1, 1/3 is roughly here, 2/3 is roughly there. So at 1/3, our point was 31 over 27. Well, 31 over 27, if you get a decimal for that, it's just a little bit bigger than 1. So that point's going to be roughly there, just a little bit higher than 1. Our other critical point was at 1, 1, so that's going to be here. And then the other critical point was at 2/3, which is roughly there, and 29/27, which is just a little bigger than 1. Now, this is not a great graph, so I'm going to go back to Desmos. And if you look at this scale, all right, so there's 1. I went up to +2 on that. Let's change that. I'm going to change this. Let's change that value to 2. Oh, I need to change this value. Sorry. I should have had this done ahead of time. That value to 2. And let's set our step at 1. All right. So at 2/3, 2/3 is going to be roughly here somewhere. We were at 31/27, which is a little bigger than 1. So the point is going to go up there. And again, I have this typed in ahead of time. There's 1/3 and 31/27. We had a minimum at the point 1, 1, and then our inflection point was at 2/3 and 29/27. So if I draw my graph, the graph is going to look something like that. Now this was a maximum. If I go back to the scribbler for a minute, this was my maximum. So this section has to be concave down. It has to look something like this. And this section is concave up, so it has to look something like that. Thank you. I forgot my phone in the house. My daughter was nice enough to bring it to me. Now she's mad at me. She mentioned, oh, he mentioned me on the film. That's what she sounds like in my head. All right. What was I talking? Let's go back to Desmos. So I'm going to zoom in on this. Here's my maximum. Here's my minimum. My inflection point is in the middle. So if I zoom in on this and then bring this graph down a little bit and zoom in again and bring this graph down, we can see here we have the concave down section. This is my inflection point where it changes, and then it goes back to concave up. So there's our graph. Now, I could label these points, but when I do that, it converts to a decimal, and that's not extremely helpful. So in my notes, you'll notice that on the graph, I did label with fractions. All right, one last example to do. So hopefully we're getting the hang of this. When we're graphing polynomial functions, it's very, very simple. Find the first derivative, set it equal to 0, get your critical points. Find the second derivative, test your critical points. Take the second derivative, set it equal to 0, find your inflection points, and then once you have the points plotted, it's just a matter of putting in the concave down and the concave up sections. All right, the last example is a little bit shorter. Well, the expression is shorter. Oh, I guess I should look at the intervals of increase and decrease. I forgot about that. Here we are. If we look at our intervals of increase and decrease, as I move from left to right, so at the far left is minus infinity, and it's increasing until we get to the first maximum, which occurs at 1/3. So it increases from minus infinity to 1/3. Then it turns around and goes down, and it keeps going down until we get to our minimum, which is at 1, 1, and then it turns around and it starts to increase forever to the right. So we have two intervals of increase, minus infinity to 1/3, and then from 1 forever to the right, which is plus infinity. So our intervals of increase, we have two of them. So we use that union symbol right here. Interval of decrease is in between. interval of decrease was from 1/3 to 1. And notice I'm using parentheses, not the brackets. We don't actually include the endpoints because there it is no longer increasing or decreasing. At that point, it is leveled off. If we look at concavity, concave up, concave down, the concavity changes at the inflection point. And this is so important to remember. Concavity changes at the inflection point. So if I go up to my graph here, the inflection point is at the 2/3. So this is where it changes right here, the middle value. So this is a maximum. It's concave down from all the way from the left to 2/3. That's minus infinity to 2/3. And then it switches concave up forever to the right. So my concave up section is from 2/3 to infinity. And my concave down section is minus infinity to 2/3. All right, last example. Graph y equals x to the power 4 minus x cubed. All right, well, let's go back to the scribbler. I want to work through this with you. Let's close that. So for the last example, let's make that black again. We have a function. I'm going to change to f of x. I like using the f of x notation. F of x equals x to the power 4 minus x cubed. And if I want to find my critical points, I have to take my first derivative, f prime of x, and that's going to be 4x cubed minus 3x squared. I'm just going to use the power rule for derivatives. And then I'm going to set that equal to 0 equals 4x cubed minus 3x squared. Well, if I'm going to solve this equation, I can take out a greatest common factor. The only factor I can take out, it looks like an x squared. So if I go to a new page, I will have 0 equals x squared is my GCF. And when I take that out, that will leave me with 4x minus 3. Now I do have two factors here. My first factor is the x squared. My second factor is the 4x minus 3. And that product is equal to 0. So that means either the first factor equals 0 or the second factor equals 0. So if it's the first one, if I take the square root of both sides, technically I should put plus or minus, but 0 isn't plus or minus. It's the point at which the signs change, so x equals 0. And if I solve this equation, 4x would equal 3. Dividing both sides by 4, x would equal 3/4. So I have two possible critical points. And now what we need to do is find their y values. So I'm going to go back to my notes because, again, this is straight substitution. I am not going to work through this with you. If x equals 0, let's get my spotlight back here. If x equals 0, that was the one point we found, and I substituted into the original function, my y value is 0. So I have a possible critical point at 0, 0. If x equals 3/4, and I substitute it in, go through all the work of simplifying the fractions, we have another possible critical point at 3/4 and minus 27 over 256. That is an ugly, ugly fraction, but that's what we got when we substituted. If we were able to get back and have a test, the test would have numbers that do work a little bit nicer than this. But when you get to the university level, these are the kind of numbers you will be dealing with. So you should probably get used to it. All right, we need to test our critical points. So I'm going to go back to my scribbler. We have these values. Now I need to find my inflection points. So to me, that's always step 3. Step 1, find critical points. Step 2, test. Oh, we haven't tested our critical points yet. Sorry. What am I doing here? We need to test our critical points. And so to test the critical points, I need to find my second derivative. Now, the first derivative was, where is it? 4x cubed minus 3x squared. So when I use the power rule, my second derivative will become 12x squared minus 6x. So let's just go back. Here it is. Here's my first derivative. The first derivative was 4x cubed minus 3x squared. So when I take the derivative of this expression, we get 12x squared minus 6x. So now I need to substitute my first critical value in. And my first critical value was 0. So if I substitute 0 in, I'm going to have 12 times 0 squared minus 6 times 0. And that's 0 minus 0, which is 0. Now, when we're doing the second derivative test, we're always looking for a positive or a negative answer. A negative answer tells us maximum. A positive answer tells us minimum. Well, 0 is neither positive nor negative. So my question is, if the second derivative test gives an answer of 0, what does that tell us? Well, that tells us something extremely important. This wasn't a critical point at all. It was an inflection point, because that's how we find inflection points. When we started this example, if you back the recording up, I was very careful with my word choice. In fact, actually, all 3 examples I've been careful with my word choice. I've always said we have a possible critical point. And that's where the first derivative test fails. The assignment you did from section 3.1. In section 3.1, we were setting up those number lines and testing whether it was positive or negative, increasing, decreasing. And there was one question from that assignment where it went positive, negative, negative, positive. And I guess if we were in a classroom face to face, I would have talked about that specific question. But now I'll bring it up. If that happens, it's not a critical point, it's an inflection point. And that's why the second derivative test is so nice. It never fails. The first derivative test can fail. And that's why from this point forward, the only thing we'll use the first derivative for is finding the critical points. We will always use the second derivative to test those critical points. So again, just to recap this, I chose my words carefully. I said we had 2 possible critical points. It turns out that one of them wasn't critical at all. It was an inflection point. So now let's go test our second value. We have our second derivative, f prime. Our second x value was 3/4. So if I substitute the 3/4 into my second derivative, that's going to be 12 times 3/4 all squared minus 6 times 3/4. And again, I'm going to save you some work. The answer is 9/4. If we go back to the notes and we test our critical values, that's what we got over here, 9/4. 9/4 is a positive number. If 9/4 is a positive number, that tells us that 3/4 and minus 27 over 256 is a minimum, and the point 0, is actually our inflection point. Now, we found one inflection point by accident. There could be others. So let's go back to our scribbler, and I'll show you what I mean. If I'm going to find inflection points, now this is the third step. Find points of inflection. So we have our second derivative, and our second derivative, f double prime of x, was 12x squared minus 6x. And to find the other inflection points, we take the second derivative, set it equal to 0. And again, I can solve this by taking out a GCF. My greatest common factor in this case is going to be a 6x. So if I take the 6x out, that will leave me with 2x minus 1. Now that seems kind of silly to have to remind you of this, but remember, when we are factoring, we're really dividing. So when I divide the 6x out of a minus 6x, I'm left with a minus 1. Quite often, it's amazing the number of students that ignore that minus 1 and just write 2x as the only remaining term. All right. I have a product. This product is equal to 0. So either the first factor, 6x equals 0, or my second factor, 2x minus 1 equals 0, in which case, if I divide this by 6, x equals 0, well, that's the inflection point we already found by accident. And if I solve this equation, 2x would equal 1, x would equal 1/2. So there is a second inflection point. So if I go back to our notes, I find the y value. So here's my two x values. I find the y value by substituting back. I showed both substitutions again. So when we substitute the 1/2 in, we get a y value of minus 1 over 16. Now I'm going to go back to the scribbler and draw this, because when we have these two inflection points, we really need to understand how this process works. So I'm going back to the scribbler. I'm going to create a blank page, and I'm going to try and make this page as big as possible. I think if I hit there, yep, there we go. All right, let's draw a coordinate axis. So here is my y-axis, and here is my x-axis. And let's label those x and y. All right, we had a point at 0, 0. So I'm going to draw a point there. I had a point at 3/4. So if this value is 1, 3/4 is roughly there. That's 3/4. And at 3/4, it was minus 27 over 256. Well, that number is negative, and it's really close to 0. If you take your calculator and go 27 divided by 256, it's a very small decimal. So if that's minus 1, I'm going to put my point there. So it's just under the x-axis. And then we had a point at 1/2. And that point 1/2 was at minus 1/16, which is even a smaller decimal. So we have these 3 points. Now, when we tested this point, it was a minimum. And when we tested these other 2 points, they were inflection points. So this is how I would draw my graph. If I was drawing this, I would say, okay, this is a minimum. That means this section of the graph has to be concave up. It has to look like that. This is an inflection point right here, which is mean the concavity changes. So this section has to be concave down. It has to have a downward shape to it like so. And then this is another inflection point. So it has to turn around and go concave up. So let's go back to Desmos and have a look at this where we can zoom in and show what happens. All right, I had the point at 0, 0. I had my point at 3/4 minus 27 over 256, which is our minimum. And then this other inflection point at 1/2 and minus 1/16. So if I go in here and use my pen to draw, this was a minimum. So we said this had to be a concave up section. This was an inflection point, so it has to change. So I'm looking at this as a concave down section. That would be my concave down section. But here, it changed again to concave up. So let's change that to my eraser. Let's erase that. So, like I said, this was concave up. This was concave down. And then this switches to concave up again. So if I get rid of those lines and put the actual graph in, I need to use this. There we go. There's our graph. So now what I'm going to do is I'm going to zoom in on this a little bit. I just want to be able to focus on this area. So let's get my spotlight here, and hopefully this helps. This point was a minimum, and because this was a minimum, it has to have a concave up shape to it. This point was our inflection. So it changes. If this part was concave up, this part has to have a concave down shape to it. Then we had a second inflection point. So it changes again. This has to go back to concave up. So hopefully that made sense. I'm going to turn this off and maybe get my pencil back out. This section here, this was a minimum, so it has to be concave up. Here's an inflection point right here. So this section has to change to concave down. Here's another inflection point. So that means this section has to change back to concave up. That's what happens at inflection points. I hope that helps. If it doesn't, rewind, watch the video again. If you still have questions, make sure you contact me. My email, kfriesen55@chinooksd.ca, or you can ask questions directly through Google Classroom. So I'm going to stop this video. I'm going to post it. This is Thursday afternoon. There'll be nothing Friday. Next week, I'll probably post another video Monday or Tuesday. We're done this chapter. So we're going to move on. And I think what I'm going to do is I might skip chapter 5 for now and skip ahead to chapter 6. So I'll think about that over the weekend and I'll let you know next week. Thanks for paying attention. Hopefully this is working for you. I think for me, we'll just keep going with it. Take care.